back to reality so that they can imagine it, you know?
Yeah. Well, yeah, so on that note, I mean, that when I first published that paper, you know, I was listening to the news. It was 2004. We just invaded Iraq, and you know,
Iraq at that time too.
yeah, and a lot of students who've come through energy technology are Iraq war veterans, and you know, I'm listening to George W. You know, kind of butcher the English language and really, you know, questioning, you know, what's the real motivation for going to Iraq. And if you know, if you look at it, the entire country is sort of shaped like an oil duct.
Oh yeah.
It was, you know, carved up after World War II. You know, the tribes that were there were not getting along, and so we sort of forced them into this political system, making it even that much more volatile. And it's just got that one little stream on the Euphrates. And this is when Google Earth was just sort of coming online. You zoom in, you're like just, you know, looking at these, you know, tankers of oil just flowing out of that pore. And I've given other talks where I look at the economics, and you can. We'll get into peak oil later, but if you look at, you know, the fact there's like something like 150 trillion barrels left of oil on the planet, approximately.
Okay.
10% of that is in Iraq, so there's 15 trillion barrels there. $100 a barrel. Well, actually, it's,
like
it's 15. It's 15. Yeah, at the time it was 100, but sorry, it's 15 trillion barrels left. 1.5 in Iraq. Multiply that by 100, so now you're at 100. So, you know, you're several $100 trillion worth of oil, and so all of a sudden, you know, a $500 billion a year defense budget doesn't look that expensive.
Yeah. Yeah, I spent 2 years over there,
Yeah.
and I don't know why I was there for 2 years.
Well,
I've seen lakes of oil,
Yeah.
like just puddling on the ground,
Yeah.
and then there'll just be a guy with a little like rug hut, and with a machine gun gardening.
Yep. Yeah, it's good
And that
stuff.
was in Kirkuk,
Black
which is up
gold.
north, and that's
Yeah.
like the third or fourth largest producing, or largest refinery in the world.
Mm-hmm.
Kirkuk, that's
Yeah.
why ISIS was so much after Mosul.
Yep. Yeah, I think that's, you know, ISIS was, or maybe still is, getting a lot of its funding from oil refineries too.
Because they're just driving right up north.
Yeah. Well, let's just dive into the course here a little bit. And I'm still having students asking me when things are due, so I promised I would cover the due dates every lecture. So here we go again. So we are at the end of week 4, and I'm just going to go right to the bottom of the syllabus. So this is week 4. We've already covered chapter 3. We're halfway through chapter 4, so I am going to launch exam 2 today. So exam 2 will be available, you know, for your viewing and taking pleasure today, and I'd like you to finish it before week 5. So that's how the due dates work in this class.
So we can just take it over the weekend? And
Take it over the weekend.
Fine.
Yeah, take it on Monday.
Okay.
Wake up at 4 a.m. on Tuesday and take it then. How, you know, whatever works for you. Yeah.
Did you want us to respond to that Will Technology Save Us video?
You know.
Because I looked at
Is
the
that
forum,
the
there
hour-long
wasn't
one?
really anywhere to type.
Oh, that's a good question. Yeah. So I guess I think I'm one of those people who tends to just, you know, like more information is better. So a lot of times what I'll do, and a lot of those discussion boards are things that students have sent me in the past that I just found interesting. And so the short answer is no. You don't have to respond to it. It's just sort of a bonus or extra. It's just kind of, you know, nice to take a look
I
at.
was kind of wondering, did they talk about that like ice in there and like what is it, like methane oxide or something?
Oh, right. Yep.
And I was wondering like why you didn't talk about that in your paper, because they were saying that there was like twice as amount of that as like oil and coal combined.
Yeah, I think so. The, you know, methane trapped in ice. I didn't know.
Permafrost too, right?
Yeah, methane trapped in permafrost. I didn't know about it when I wrote the paper, and just to follow up too on that summary 1 paper.
And then like when I was watching the video, I wasn't sure because he converted everything to like the same units just like you did.
Oh,
so it was,
okay.
Comparable.
Yep.
And then I wasn't sure if he went away from that and was saying that there was just like twice the amount of that ice as coal and oil combined, or like in abundance wise, or like actual like energy?
It's a good question. I don't know the answer. I don't know how much methane is trapped in some of these frozen deposits or solid deposits.
Talking about melting down ice to get methane out of it?
They just, it's like ice, it's already there, methane already is like trapped in it underwater, and they just like, you can literally just take it, stick a lighter to it, and just
Well,
like.
I was just
it's
thinking there's
flames.
videos all over the internet. Like there's like a
Yeah.
little bubble, they pop it and then they put a lighter
Yep.
to it.
Yep.
And then it's like,
And it's like, yeah, it's
but then
naturally.
eventually it'll just fizzle out like within like 5 or 10 seconds
Sure.
usually.
Sure.
That might be not so good for ice.
No.
Well, it's naturally.
Kind of a thing.
It's
Yeah.
naturally
Well, it's like-
happening though, like it made
Yeah,
itself.
so
and
the
then
the
we just-
methane is happening naturally, but us extracting it could lead to other issues.
Well, there's
But either way.
there's a lake up in Canada that's completely frozen solid, and there's methane bubbles, so you can see like the
Yep.
bubble rings
Yep.
coming
Yeah.
up through the depths.
Yep. Yep.
Yeah, even in the oceans.
Oh, yeah, yeah.
Well,
Well,
They're
ocean
gonna
and
go after the
seafloor,
water
and then it comes back.
and
That's how
ice.
they think all the ships sink, because methane will start to like make the water thinner, I guess, or whatever, however any ships will sink. So that's why they think.
That's crazy.
That's why they think the Bermuda Triangle.
Oh, really?
Yeah, they're hearing like methane.
Oh,
pops or-
methane bubbles
Methane
reduces the
bubbles,
density of water? That's
density
an
of water,
interesting
the
theory. I'd
ship
never
will
heard
sink.
that.
Just like, I mean, because at that point, you're just thinking like, you're flushing a toilet. It's not like you're slowly sinking.
Oh, that's a trip.
Yeah, just.
Okay, so everybody's clear. And you know what I've done? I've just allowed exam one to remain open. You know, I think for whatever reason, and I've even heard this before. You know, I've heard students log in and say, oh, well, I was trying to avoid watching the lectures. Like, just don't say that to your faculty member. Like, you know, I'm here, I'm paid to do this, you know, so don't say, oh, I forgot to, or I was planning on not watching the lectures this semester. Well,
What? How's that make sense?
I don't know.
That makes sense.
I don't know. So anyway, you know, the point of giving lectures is to, you know, update you and help you through some of the materials. So again, I will launch exam 2 today because this is week 4, and I'd like you to finish exam 2 before week 5, which starts for this course anyway on Tuesday. Okay. So, and again, so I've given extra time for exam 1, given extra time for summary 1. You know, this is really for your benefits, so it's not week 13 and you still haven't taken exam 3 and problem set 2, and et cetera, et cetera. So, okay. Well, let's get into the chapter. And I started through the notes here. I'll just give a really quick overview of what we've done up to this point. We started off with Newton's laws. Objects in motion stay in motion. Sum of the forces is 0. Force equals mass times acceleration. I showed you the difference between units and dimensions. So, you know, the units are all human-made. The dimensions are there, you know, divinely made or just naturally made, or however you want to think about it. You know, there's mass, there's length, and there's time. We just pick, you know, newtons or pounds or kilograms or what have you to measure these things. There's convenient little packages. I then took us from force, which I think we kind of understand. We mentioned the fact that it's a vector. Distance is also a vector because you can go in 3 different directions,
X, Y, Z.
X, Y, and Z. This thing is a dot product, technically. It actually takes 2 vectors and turns them into a scalar. Energy is a scalar. Energy does not have a direction. Heat doesn't have a direction.
Unless we funnel it or whatever.
You could have kinetic energy moving in a direction, but then that's actually when you get into momentum, which is a vector.
Well, doesn't heat rise?
Heat does rise, but heat itself does not have a direction.
Well, you're talking about in your paper about like capturing the heat from the engines, and wasn't that in your paper or was that from Joe?
It was, well, you're just saying that there's like wasted heat, like most of our
Yeah.
high energy from gasoline just gets burned off as
The
heat.
run off as heat,
Yeah.
so you could collect the.
So if there was a way to collect it.
Yeah, a lot of times you'll see in some power plants, you don't see it that much in the U.S., but combined heat and power, where you're instead of just releasing that heat to the atmosphere, you're injecting it underground for melting snow on sidewalks or, keeping homes warm, et cetera. A little more of a challenge with the car, to like inject the heat from the automobile into the ground. I mean, you might think of some solution there, but that's a trickier one. We also derive power, which is also a scalar. And I'm putting these lines under here, and if my engineering colleagues were looking at this, they'd probably be cringing, because typically a single line means a vector and no line means a scalar. Power does not have a direction either. I'm just underlining to denote what I'm talking about. Velocity, of course, has a direction. You can go forward, backward, up, down, right, left, etc. And then I showed you these are the dimensions for energy and power, which we'll rely on heavily throughout the course. I also told you that energy and work and torque all have the same dimensions, which is mass times length squared over time squared. I even did a little bit of calculus and showed you that energy equals the integral of power over a per unit time, and I gave you a little picture to show that too. So something that's very powerful is gonna blast off, sort of high and short. Something that's less powerful is going to take a little longer, but all that space under that rectangle as we move through time is the energy converted. We did a neat little derivation. This was from the book, showing how much energy is in a given volume of wind blowing through a wind turbine. If you know the volume, this is big V for volume. If you know the diameter of the turbine, here's the turbine. Then you can figure out the mass of the air, because we know the density of the air. We can then shove that through the kinetic energy equation. So this is really the first type of energy I introduced you to, mechanical kinetic energy. And then we converted that into power by dividing by time, which in this case was 1 second. And we said air moving at 9 meters per second through a wind turbine with a diameter of 60 meters could crank out 1.33 megawatts in a perfect world, if all of that energy were converted into electricity. Pretty soon we'll see that no machine, no system is 100% efficient. Some of that is lost, wasted, not recovered, however you want to think about it. So there we go. Second type of energy I introduced you to is potential energy. This is also mechanical energy. Kinetic energy is mechanical. Potential energy is also mechanical. And then we just briefly looked at that dam example. I talked a little bit about the Gordon Butte project, which is a pumped storage, sort of an advanced hydro system. And I showed that in that case, the more mass you have, the more gravity you have, and the higher the dam is, the more energy you have. E equals mgh. So that's also mechanical energy. Then we did mechanical power. We talked a little bit about James Joule. He was a crazy man until Kelvin said he wasn't, and said that if we spin something with a given torque at a given angular velocity or speed, we're going to get some power. All that mechanical power, that's spinning, so you can think of that as a third type of mechanical energy, sort of some machine spinning, that will then be converted into heat. So again, energy equals power times time, energy equals torque times angular velocity times time, and all of this mechanical energy, again, sort of rotational mechanical energy, can be turned into thermal energy. So first time we've really talked about that. So this is the heat capacity, or the specific heat capacity. We looked that up for water. It's 4.2 joules per gram per Kelvin. If we know how much of it we have, and we know how much the temperature changes, then we know how much heat is there. I talked about the fact that heat and temperature are very different things. Maybe later we'll get into intensive and extensive properties, or intensive and extensive properties. We can get into that later, but anyway, they're very different things. Okay.
Temperature?
Yes.
So temperature is just a way of measuring heat? How much heat?
Temperature is a way of measuring heat, and I'll take one little sidebar here, if I may. So if you remember Boyle's equation, we know that Boyle's equation is PV equals N RT. This is the ideal gas law. We know that R is just a constant. So P is pressure, V is volume, N is the number of molecules in your system, and R is a constant. We can simplify that and just say that P, and again, that's a little p, that's a big V for volume, equals NT. Because the R is just for keeping track of units. And I can do that one more time and say that T equals PV over N. Now, as it turns out, pressure is actually energy per volume. That should make sense. So if you think of a balloon and you keep jamming more pressure into it, you're putting mechanical energy into it. So pressure is energy per volume. There it is. Well, energy per volume times volume just equals energy. Temperature is energy per particle. And if you get right down to it, it's just how fast each little molecule is moving. So if we get right down to the molecular level, here's an oxygen molecule, flying through the atmosphere. Kind of weird thing about air, I just realized the other day, the individual molecules in air are traveling, on average, faster than the speed of sound. Now, it might sound kind of weird. They're not going very far. They're just bouncing around faster than sound itself travels. Something to think about. But that's all temperature is. Temperature is energy per particle, and as it turns out, it's just, the energy of the molecule just equals 1/2 m velocity squared. The mass is tiny. The mass is just a few daltons or whatever, but there it is, bouncing molecules. So that's what temperature is fundamentally. Yes?
It's more of a dispersed environmental version of heat, and then heat's condensed in a more concentrated form.
Well, is molecular motion a more dispersed environmental thing? Yes and no. I mean, it just kind of depends how big you are. I mean, if you're a little bacteria, in a petri dish, yeah, the molecule flying at you is your environment. At our scale, molecules are bombarding us at the speed of sound all the time, but you don't feel them. You don't feel them battering you around. You just feel heat. You just feel you get warmer. Yeah, yeah, yeah.
Sorry, what did R stand for? in relation to-
R is the ideal gas law constant. What's the name of it? I think that's just all it's called.
I just said constant.
Yeah, it's just the ideal gas law constant. And this is the ideal gas law. So that hopefully it's just a little sidebar to answer your question about the distinction between temperature and heat. Okay, then we got into electrical energy, and it's sort of easier to approach electrical energy from a power standpoint because we all understand current. We talk about how many amps flow through our technologies, and it's easy to think about voltage because we got 110 volts in the house or 12 volts on your laptop. So current times voltage is power. We did a little example and said for a refrigerator, it might be running at 770 watts, which incidentally is about 1 horsepower.
That's why I like in your article.
Not a horsepower, so tie your horse up to your fridge and feed him some hay. It'll keep your groceries cold. We then said let's let this fridge run for a minute, 60 seconds, and we're going to convert 46.2 kilojoules of electricity into thermal energy, or sort of anti-thermal energy. We all know that thermal energy is still going to come out the back end of the fridge. We're still heating the house. I mean, just go put your hand on your fridge. Heat's coming out. You're converting it to heat. Had an interesting conversation last night. We're hosting some delegates from Tohoku University in Japan. It's sort of one of the more prestigious technical universities. I was just there in June. There was a professor who's made 49% efficient solar cells. Right now, like the ones behind you there are 15, 20. Some of the best models on the market are maybe 30. These guys are knocking on 50%. And on the way down to dinner, I mentioned to one of my colleagues that someone just donated an electric car to the program. He said, "Oh, you got a coal burning car." I said, "Well, I suppose, because a large fraction of Montana's electricity comes from coal, but not all of it. Northwest Energy bought the dams so that they can meet their renewable energy standards that they have to. They're purchasing wind. I had the opportunity to go to their headquarters there in Butte. It's kind of like a big episode out of Batman where you got the lights and the Situation Room and all that. But yeah, so certainly some fraction comes from coal, but an increasing fraction comes from renewables. Yeah.
When you're talking about 50% collection, is that at the equator? Is that at like what degree in the hemisphere are you talking about?
50% collection of what?
Of the sunlight, the solar?
This is the efficiency of the technology.
Oh, okay.
Yeah, you
Okay,
stick it out in the sunlight, and 50% of the photons activate electrons.
Okay.
Yeah.
Okay, got
Yeah.
It's like it would be putting out more closer to the equator, but
It would put more out close to the equator.
it's just taking 50% of wherever.
Exactly.
Okay,
Exactly.
I understand now.
And it's a little more complicated than that because the technology they're working on actually has multiple layers and can capture photons of different energies. So they're working with germanium. If you look on the periodic table, you'll see that germanium's sitting just below silicon. So there's different semiconductors that will absorb photons at different frequencies. Exactly.
Okay.
Yeah. If you take 102 in the spring, we'll cover that in more detail. Cool. Great. Okay. And then we went over this little law that says voltage equals current times resistance. And we kind of jammed that into the power equation. We saw that power equals IR squared. Well, what's going on with that? What is that becoming? What is this IR squared becoming? Is that a good thing, a bad thing? Is it wasteful? Is it useful? Well, it's turning into heat, and if it's making you toast in the morning, it's useful. You want resistance. You want high resistance in your toasters where it gets hot. Or if you're running incandescent bulbs, you want your tungsten to get hot and have high resistance, so light gives off. If you're running power lines from Colstrip to Seattle, resistance is bad, because you're wasting all that electricity as heat. So now what we've done here, again, conservation of energy, we've combined electrical energy with thermal, and we'll do this all day long. You just can't kill energy. It's gonna go somewhere. Okay, so let's get into the rest of the chapter. There's some really good stuff in here. I think we got through figure 10. Yep, there we were with electrical. And again, we talked a little bit about chemical energy last time. We looked at the dynamic periodic table, showed that every single element has its own electronegativity, its own affinity for electrons. As those electrons are exchanged between the chemicals in batteries as they flow from the cathode to the anode through whatever filament you might have, or they're flowing through a gas in the case of a fluorescent, or they're flowing through a diode in the case of an LED light-emitting diode. Anyway, the electrons physically flow through that. The chemistry that you've neatly packaged eventually decays or degrades or whatever. Your battery's dead, and then you start over. So there we are, converting chemical energy into electrical, into radiant, into thermal. There we go. So this is just the engineering or technical signal for a battery, plus and minus, schematic, exactly. There's some voltage on there. And one thing that's definitely worth mentioning, let's just make this analogy here really quick. So let's just go mechanical versus electrical. And we know that in a mechanical system, as we looked at last time, the energy equals the force, however hard we're pushing, times the velocity. Times the distance. Times the distance. Power is force times velocity. And for, actually maybe I want to do it the other way. I'm sorry, let's just back up and do it. It's easier to do with power. Let's just do it with power. back up one second. Easier to do with power. Okay, so in a mechanical system, power equals force times velocity. In fact, like I said before, force is a vector, velocity is a vector. That's actually a dot product. I won't hold you to that, but power is a scalar. We'll do the same thing. That's mechanical, and here's electrical. P equals, and I'm going to write a little bit differently than I did before. It's the voltage times the current. Sometimes it's a little I, sometimes it's a big I. And I've written it in this way because voltage and force are similar. They're pushing. And velocity and current are similar in that they're moving through the system. So current, think of motion, velocity, think of motion. And this is true in any system. And you can use it for hydraulics, you can use it for wind systems. This variable right here is called the across variable, and this variable is called the through variable. The across is sort of pushing across space, and the through variable is moving through space. So hopefully this ties these two things together. This is mechanical, and this is electrical. Okay, so just something to keep in mind as we're exchanging between different energy types. Okay, so there's the schematic, and then the resistance, like I said before, can be a good thing if it's a toaster. It can be a bad thing if you're actually trying to push electrons across continents. Okay.
It's a bad thing if it's your body.
Bad thing if it's your body, yeah. If you go and grab hold of a live wire. Yeah, I guess if you had really good resistance, it would just pass through and not hit your vital organs. But yeah, really low resistance. Okay, so again, this is a picture of a battery. There's an anode and a cathode. We looked at electronegativities last time, and typically what's happening. Actually, let's look at that in a little bit more detail, and we can just kind of look at Na, and let's just look at Cl for a second, and let's just bop out to the dynamic periodic table briefly. Let's look at sodium. Let's look at chloride. So here's chloride, and I always like to go back and just look at the orbitals. So chloride has that one little extra electron sitting in the 3p orbital. I don't know if you can see that. It's sometimes hard to move this mouse off of that chloride, but maybe I can just kind of wave the. Yeah, it's kind of tough to wave it over there, but just right here, just keep your eye on these little two boxes right here when I look at chloride. There's that one extra electron sitting out there, sort of like a free electron. We talked about metals last time, and you've got these electrons that are way far away from the nucleus. They're not attracted to the protons, and those are the ones that are conducting in metals like copper. Over here in sodium, it also has that one free electron in the 3s. Now, the 3s versus the 3p, that 3s is a stronger attractant for that free electron. So that sodium is going to pull that extra electron towards it. If the chloride pulls an extra electron and fills it up, it's going to get this negative. So let's just say the electron goes towards the chloride, it's going to become negative. If sodium loses an electron, it's going to become positive. So that's why you typically see those ions written like so. So if that extra electron travels, and let's just do it this way, that extra electron is actually going to travel sort of up through your light bulb, etc. But down in the battery, it's the ions themselves that are moving. It's the larger atoms and ions that are actually sort of moving back and forth. So again, kind of think of it as, conservation of matter. But that's what's going on inside any battery system. The electrons or the free agents kind of flying through the electrodes, and then the ions of the atoms themselves are moving inside the battery.
So the two elements just exchange electrons back and forth until they both agree, basically?
That's exactly right. They exchange electrons, and they sort of exchange each other, too. They're
So-
actually moving.
So
Yeah.
like with the rechargeable battery,
Uh-huh.
does it just put like ions or like electrons back in?
It does.
Or-
Yeah, it shoves those electrons back and forces the ions back apart.
Okay.
Absolutely.
But it's even like a rechargeable battery will eventually die.
Yeah, and so, right, and that's, there's a lot of engineering that goes into batteries. And you can kind of, and one way to think about it, you could think about it as like a highway system or a little city in there with little roads where, in advanced batteries anyway, in a car battery, everything's kind of just sloshing around inside a liquid. But, eventually the cars wreck, the asphalt degrades, things get clogged, whatever, and we don't really have the nano machines to go put them back. We're always interacting with these things from large, jumper cables and chargers and things like that. So, there's no technology I've seen that's immortal or infinite. Yeah. All right, so the next fellow here, and then as soon as I cover this, we'll take a break. Next fellow we see here is Michael Faraday, son of a London blacksmith. If you ever get a chance, go and check out Neil deGrasse Tyson's lectures on cosmos. He talks about Faraday really being a showman. He would go on stage and show, arcs of plasma flying around, use his body as a conductor, and show the electromotive force. He was able to show that magnets and electricity were related. What he lacked, he didn't have the mathematical background to really understand it on a fundamental level. We'll see Maxwell here in a second who tied that together. But
So you like a pre-Tesla?
you could think of Faraday as a pre-Tesla, yeah, in a lot of ways. Yep, absolutely. And so there's Faraday's law. You can take a look at it. There's also Sir Humphrey Davy, who was sort of taking notes. So Faraday was kind of the showman, the experimenter, if you will, the backyard tinkerer. And Davy's like, wow, something's going on here, because it's hard to see electricity, unless it's like turning into light, and you can't really see magnetism unless it's spinning a compass or something like that. These are very strange unknown forces to these guys back in the day. Yeah. Popular lecture found in the Friday evening discourses, which continue today. I guess this is back in jolly old England. So it's a little chunk of history there. Okay, so let's take a break. It's a little bit after 10. Wow, what just happened there? That was a transform the whole periodic table unknowingly.